Oh hey, it's me again, your favorite chemistry teacher. I'm going to start talking about nuclear chemistry. So I've had some trouble with these videos because it keeps running out of batteries and not warning me really. So that's why there's probably going to be 2 of these. So in topic 3, nuclear chem, we're going to talk about nuclear decay, instability, half-life, artificial transmutations like fission, fusion, etc. Okay, a lot of this is just stuff that you need to see, so print one of these sheets out. You can find it on the website and follow along. Okay, so we're going to start here right away, okay? Alright, so a natural transmutation is spontaneous disintegration of the nucleus, so spontaneous breakdown of your nucleus into a nucleus of a different atom. So there are a bunch of types in nuclear decay. Alpha, this is an alpha particle, 42He. What you need to know about it is it's a particle, not a ray. Weak penetrating power due to large size, comparatively. So if you're asked to write a nuclear decay equation for uranium-238 through an alpha decay, you would start by writing 4,2He, which is your alpha particle, plus, and then you just want to make sure mass and charge lines up on both sides. So 238 minus 4 is 233, and then we have 92 minus 2 is 90, and so from there you go into your periodic table. Let me get one pulling up, and you have to look up the bottom number, which is your atomic number. So let's pull one up. So number 90. Whoa, sorry guys. I'm not that good at this. Number 90 right there, TH. Okay. Next one, we have beta, 0 minus 1e. It's a particle, it's like an electron. So we have 14C, 6C, and we are going to do a beta decay. 0 minus 1e, which is your beta particle, plus 14, and then just careful because 6 minus negative 1 is a positive 7, which is nitrogen. This seems like it's going to be blurry. Okay, positron decay is when you give off basically the opposite of an electron. So we have 8,5b is going to give off a 0 plus 1e plus, so 8 is going to stay the same, 5 minus 1 is 4, and number 4 is beryllium. Okay, electron capture is when you have the nucleus capturing an electron. So right here we have 18,9F plus 0, negative 1e. So this looks like a beta particle. It's only going to be a beta if it's given off. So this is going to be an electron capture. So that is going to make 18. 9 plus negative 1 is 8. So number 8 is oxygen. Okay, and then we have gamma. Gamma is a high energy ray. It has the greatest penetrating power. It's really strong. It can get through a lot of stuff. These are really going to mostly occur in other forms of nuclear decay, so it might be a byproduct of a positron decay or a beta decay, something like that. Alright, nuclear stability. Nuclear stability is basically, the goal is to have a proton to neutron ratio as close to 1 as we can get. Atomic numbers from 84 and higher are naturally radioactive, and to decide what kind of decay you're going to have, this is just a general rule. So if the mass number is greater than the atomic weight on the periodic table, you will have a beta decay. So for example, if you have 16,6C, you know that carbon is normally 12 on the periodic table. So 16 greater than 12, beta decay. Okay, if your mass number is less than your atomic weight, so for example we have 11,6C, where the mass number 11 is less than your atomic number on the periodic table, or atomic mass on the periodic table, 12, you will have positron emission or electron capture. Atomic numbers higher than 60 are typically alpha decay because they're big. So the goal is they want to reduce that proton to neutron ratio or increase it to get it closer to 1. Okay, so here we go with half-life. I think half-life is really simple to kind of just think through, but sometimes that stresses people out. Half-life is the time it takes for 1/2 of a substance to decay. So let's say we have a sample mass of 120. That means we're at 100% radioactive. Time 0, half-life 0. If we go through one half-life, let's say time is 10 seconds. 50% will remain, and you'll have half of your original sample, so 60. Let's go through a second half-life. You have a total now of 20 seconds. 25% remain, and you have 30 grams. Go through a third half-life. Now your total time is up to 30 seconds. You're down to 12.5% radioactive, and you have 15 grams of your sample, radioactive sample left. So on the AP exam, if you get a half-life question in the multiple choice section, you should be able to just kind of think these through. You might see a half-life question when they're talking about kinetics, like in a part 2. Radioactive decay is a first-order reaction, so you have T1/2 equals 0.693 over K, which is derived from this equation that's in your reference table, ln of N naught, the original concentration, divided by N at T1/2, which is the concentration of at the half-life, so half of your original, equals K times T1/2, where T1/2 is your half-life, the time of it, and K is your rate constant. A couple things, half-life never changes with changes in the environment. It's always going to be the same thing. Alright, artificial transmutation is the disintegration of the nucleus by bombardment of a high energy particle. So, usually you're going to see something like uranium-235 92U. You bombard it with a high energy neutron, 10N, or you might see 239 94Pu plus a high energy neutron. When controlled, you have nuclear energy occurring. When uncontrolled, when you have an uncontrolled chain reaction, you have a nuclear bomb. So the problem is that the waste from nuclear fission has a really, really, really long half-life, and we don't really know what to do with it. There's talks about perhaps putting it in the Yucca Mountains in Nevada, so digging deep into a dry, mountainous area and putting it in, appropriate containers there. But there's some debate over whether that's good or not. The other one is fusion, that you should know really well. That's when you have two hydrogen atoms fusing together to form helium. So you have two light atoms coming together to form a heavy one. Fusion is clean and inexpensive, which is good. Its waste is clean. The problem is it's really hard to combine two hydrogen nuclei together because they have repulsive forces due to their positive nucleus. So it requires a really high temperature and pressure. So here's two nuclei coming together to make a 2+ nuclei. Really hard to do. Mass defect says as the two nuclei combine, some mass is converted into energy. So if you actually take the sum of the masses here and the total mass here, they're not going to be exactly equal because some of the mass from this side has converted into energy. If we talk about the reverse, going from this nuclei, splitting, the energy it takes to split it is called the binding energy. So those are kind of just two similar things. Combining it, mass defect is saying some of this mass is converted to energy. Going the reverse reaction, the energy that you need to split up this nucleus is called binding energy. And that's it for nuclear. If you want any more information, take a look in your review book. Has a bunch more than what I just went over, but this should be good enough, I hope. All right, until next time.